Hello everyone, my name is Bob van der Donk. I'm the tech lead for Inventor in product support here at Autodesk, and I will talk to you today about the stress analysis module in Inventor 2010. Here is an overview of the topics that I wanted to discuss. First of all, how do mechanical designers use finite element analysis packages? I want to illustrate this with a very simple bookshelf example. And then we move on to some key concepts of FEA, more specifically the mesh and what Inventor does with global and local mesh settings. And finally, I will talk about convergence quite a bit, and more specifically H&P, adaptive refinement. Let's concentrate on the bookshelf example. So here is a very simple bookshelf which you see on the left side has a design with 3 supports, and on the right side I have 4 supports. Which one is better if I want to use this bookshelf for a series of books with a known weight? Well, one of the first things to ask ourselves is what material could we use? Do we use aluminum versus steel, or a more focused question here, if we think that our books have a total weight of 5 kilogram, what geometry will satisfy this criteria before the bookshelf tumbles down? So we will go into this in more detail in the following slides. How do designers use FEA? Well, they have very specific goals in mind, and first of all, they want to validate their design. Here are a couple of questions that you might want to ask. Is my design strong enough? Or in other words, is it under-designed? Will it fail under heavy load? Is it prone to resonance in vibration circumstances? On the other side, you could also ask yourself some optimization questions, and then if my design is working correctly, could it be that it is over-designed, that I use too much material for the task? Or can I achieve the design goal by using a slightly different geometry? And finally, can I get to that same design goal by using different materials? These are all very interesting questions, and I will illustrate some of these in the remainder of the presentation. To answer the strength question, it is sufficient to run a default mesh and a default analysis, and let's assume we get a result like the picture that I'm showing here, where the stress analysis gives us a minimum safety factor of 8.88. What this really means is that if we consider an estimated weight of 5 kilogram, that we would be able to support 45 kilogram of books on this particular bookshelf. It might not be very obvious, but the reason, the location to find this minimum safety factor is to look on the colored bar and look for the word or the abbreviation min behind the number. I didn't spot it originally, so someone had to tell me, so I prefer to tell it to everyone here as well. So look for the word min behind the number. That gives us an idea. 8.9 safety factor, of course, is a very safe factor. Probably in industry you would probably more shoot for a 2 or 3 times safety factor to not over design your particular assembly. Here is the initial situation with our bookshelf. So we want to do a first validation with the default settings and see how the bookshelf reacts under a vertical load of 1500 Newton. I'll show you the load here in a second. So it's 1500 Newton going in the minus y direction. We took aluminum as the material, and we have a couple of constraints. So we have a fixed constraint here and a fixed constraint in the middle of the bookshelf. So nothing peculiar, we just run the simulation and see what the maximum stresses will be and what the safety factor is. So I have a maximum of 29 megapascal, and the safety factor initially is something like 9.46 in this case. So we'll keep that value in mind because we will do some iterations around the safety factor later on. Now that we know that our design is safe, we want, of course, to optimize the design so that we use less material or less thick material. In the image that I'm projecting here, you see the setup that comes from the parametric table command. So in this particular example, we are looking for an optimization with a safety factor that stays above 2, but where the mass stays below 5 kilogram. So you see here on the limit column here, we entered our limits for the safety factor and the mass, and you see here the result value. So our safety factor here is 2.37, which is higher than 2, which is fine, and also our mass is 3.57, way below 5. At the bottom you see the parameters that we actually were varying between certain values. So we changed the support thickness between 2 and 5 with increments of a value of 1 millimeter, and the board thickness we varied from 2 to 4 to 6. And you could also slide these values to give you a little bit more comfort in doing so. The second scenario I want to look at is the optimization scenario. So I have a new simulation here in my browser that I called Optimize. So what am I trying to optimize here? Well, my safety factor in my first validation revealed that it was relatively high. So how can I still be within the correct safety factor limits but reduce the thickness of my shelf and the thickness of my support? So I want to obtain an acceptable design with less material. So in order to do that, I use the parametric table function here. So initially it's empty, of course. So in the first half I need to define design constraints that are valid for the entire assembly. So I'll add a couple. So I want to, of course, lower my mass. So right now I have no idea what my mass is. So let's have a quick peek in the eye properties to have an idea. So I'm going here to the physical calculation. So my actual mass is around 10 kilograms. So okay. So I go back to my parametric table and I say I want to have an upper limit of my mass of 7 kilograms. So that would shave off 3 kilograms from my actual mass. And then the other constraint that I want to include is the safety factor. So I still want to be safe, of course, so I put a lower limit of, let's say, 2. How will I influence my geometry? Well, I will play with some user parameters that I get from my component. I cannot get to those parameters from this dialog, so I need to do this in the context menu on the individual component. So first of all, on the board component, I show my parameters, and I've predefined a user parameter here called board thickness. I include this one, and I'm also interested, of course, in lowering the thickness of my support. So I do the exact same thing there, and I include the support thickness parameter in my calculation. Once I've done that, you will see that my parametric table is populated with those values, and it's showing the actual values here. So in order to save material, I have to reduce the thickness, so I'll reduce that in discrete increments of 1 millimeter. So for the board, I take 3, 4, 5, and 6 as possible values, and for the support, I take 2, 3, 4, and 5 as possible values. So with that input, I can now launch a calculation, and in order to get all possible solutions, I must not forget to select the exhaustive set of configurations. This of course will take a little bit longer, but this guarantees me that all possible combinations are calculated. So we'll kick it off and have some coffee, and then we'll come back. Here are the results of the calculation and the optimization. So we'll have a peek in the parametric table, what it's telling us. So, and let's have also a look at the values here. I do want to show the values of the support thickness while I do this. So in the parametric table, you see that my mass is definitely over my limit with 6 and 5 as thickness. So I can start sliding this slider here and see what this gives for my mass. So this lowered my mass, but still insufficient. So if I reduce the board thickness to 4, you will see my mass is lowering slowly to what I was hoping for. So I have now, in this case, this would be an acceptable compromise. So with a board thickness of 5 millimeter and a support thickness of 5, I would still have a safety factor of that's higher than 2, and my mass would be even lower than 6. So I could still start playing with the thickness of the supports, and you will see that my safety factor now is violated. So I bring up my board thickness. So you see what I'm trying to do here. You can play with certain variables, and once you're happy with the combination and it meets your design criteria, you can just say generate this configuration. Okay, so this will generate a board thickness of 4, so and a support thickness of 3. In a similar manner, we can of course also optimize the material, so we can do what if situations with alternative materials. You see an image here of what I did here with mild steel and carbon steel. So you can just select different materials while you before running a new simulation, and you can do this with the assign materials command. In the third scenario, I want to examine what the effect is of the material choice on my safety factor. So the original material choice that I made is an as defined, so I just use the aluminum as specified in the different components. There's no override in the FEA environment whatsoever. The results of that calculation with a force of 1500 Newton, I just want to verify that, is something like 9.47. That's my safety factor here. So if I change the material to, let's say, a plastic material, would my bookshelf still hold the load? That's the question. So I take a polycarbonate here and I just rerun the simulation, and we'll see what that does. I expect the safety factor definitely to go down, but is it still within acceptable limits? That's the question. So my safety factor at this point is 2.33 millimeter. uh, which is probably limit. So um, that's a type of simulations you can do quite easily with our software. Before doing any further demos inside the product, I wanted to take a couple of minutes to explain a couple of key concepts in FEA. The first one and the most important, of course, is the meshing and how you mesh. Uh, Next, I will talk about convergence in your results by using H refinements or P refinements. And not discussed today, important to know is also the contact types that are involved in your design. This might be the topic of the next presentation. Inventor 2010 uses a tetrahedral mesh. You see an example of that on the right. The mesh settings can be influenced by going to the stress analysis settings dialog and going to the meshing tab. There are several values that you can modify. The one that I want to draw your attention to is the one that's called maximum turn angle, which you see here. I've set it here to 10 degrees. So what's the effect of changing the maximum turn angle? Well, the best I can show you is by saying that the maximum turn angle on this case on the right is 60 degrees. This is a combination of a circle on the inside and a rectangular shape on the outside. If you change the maximum turn angle to 10 in this particular case, you will see that the succession of tetrahedral meshes is much more dense on the cylindrical face compared to the planar faces, and that's really, I think, conveys very well what the effect of this max turn angle is. Here is a big caveat on doing FEA calculation out of the box without thinking deeper. So default FEA results can be wrong, and I use a very simple example here with a weldment assembly. So in this slide you see here that on our initial calculation we obtain a maximum stress of 58.8 kSI, and that's the situation where we have weld beads being present. If I compare this to a slightly different situation where I remove the weld beads, I obtain a maximum stress level of 47.4. Intuitively, you would expect the stress levels to be higher when the transition is more like a straight corner transition versus a filleted type of transition, which is the case for a weld. So why do we see the result? Well, the answer is simple. You see this difference because we did not use any convergence yet. Convergence can help you improve the accuracy of your stress results. Let's have a look at this assembly. This assembly is an weldment assembly actually. So there is one single weld bead between the two parts, and the bead type I use is concave. Nothing other is of interest in this assembly. So let's have a look at the stress analysis environment. So what we're trying to solve here is the stress levels in between the two parts when there is a vertical force present. So I've defined a load of something like 1,000-pound force in the Z direction. I've also defined some materials here, so to make it easy on myself, I just reuse the materials as defined in the IPT files. There is also some constraints that I created on the faces to keep the part fixed in space. So there's one fixed constraint on this face and another fixed constraint over here. You also see that I have two particular analysis incorporated in this browser. One that is called with weld beads and the other one is called no weld. I think from the name it is clear what I'm trying to do here. I compare two situations. The no weld situation is where I, I eliminate the weld bead, and I can do so by using the exclude from simulation context menu. So the weld bead is out of the picture here, and if I do this, I expect to find intuitively higher stress levels in the no weld situation compared to the situation where the weld is included. So let's verify this intuitive rule. So I go back to the no weld setup and I run the simulation, and we'll see what we get here. So the bar on the von Mises stress tells me that the maximum stress in this area here is something of 45 KSI. I want you to remember this value because we will compare this value with the other setup. So if I now go to my other situation where I include the weld bead and I run the simulation again, I get slightly different result, and the value here is 58 KSI, which is remarkably higher than the 47 in the other case. So why do we have a difference here, and certainly a result that is not conform to what we were expecting? For the answer, I need to explain something first on convergence, and then we will give you a second video with the answer to this question. So stay tuned. Let's talk a couple of minutes about convergence. So I will give some definitions and some settings. I'll also talk about the process that's involved, and finally I will give some more details about the convergence plot that we can get at the end of a calculation. First of all, the refinement settings. There are two refinement methods. However, only one is exposed in UI. So if you look at this convergence settings dialog, you will only find references to what we call H refinements. And there's another one here on H refinements. But in fact, there is a second one under the hood. And we call that second refinement method the P refinement method. It's included automatically for you. You cannot set anything on it. The H refinement, however, is a number that can be set. By default, you see that it is set to 0, and the convergence plot is not visible when you set H refinements to 0. Keep that in mind. Both refinement techniques are used simultaneously, and we are very proud of that because it gives you a very good results in our opinion. So like I just said, there are two refinement methods, the P and the H refinement. The P refinement, in fact, increases the polynomial order of the shape function that we use in our calculation. It does not change the mesh element size. It's another important thing to remember. The H refinement method is in fact the diameter of the circumscribing sphere around the mesh element. And you see like an illustration here. I try to visualize it. It might not be exactly mathematically correct, but at least it helps you focus the idea. And then finally, what I want to say about H refinement is that this method really reduces or can help reduce the mesh element size. The refinement of the mesh can either be done across the model in a uniform fashion or non-uniformly, what we call adaptively. You see here an example where I have a mesh on the left that by default has an H refinement set to 0, when you start increasing the H refinement value, you can get to a result on the right for an adaptive mesh. I also wanted to point out some differences between the convergence process when applied to a part environment or an assembly environment. There are slight differences. For a part, we use this type of convergence plot. So the first three solution steps that you can see at the bottom of this convergence plot, I marked them P1, P2, P3. Those steps are P refinements. Once we add H refinements for the next solution steps, the H and P refinements are used in combination. So H refinement only kicks in after step number 3. If we compare this to the assembly environment, we kick in the H refinements a little bit sooner. So the first two solution steps, which you see here at the bottom, are P refinements, and then the H refinements kick in on step number 3. I've shown you already the convergence plot in the previous slide, but I wanted to come back to one particular detail on the plot. It's in fact the convergence rate. The convergence rate is the maximum delta percentage-wise that you want to obtain between two consecutive calculation results. So in this case, between step 4 and step 5 result, I do have a convergence rate of 1.336%, though the results don't deviate more than 1.336%. If I combine the convergence settings dialog with what you get on the plot, I wanted to illustrate the influence of the stop criteria here. So the stop criteria that I had given in this particular case is 2. So you see that although that I gave 7 steps in refinement, it did not finish all 7 because it was stopped out earlier because of this criteria on the convergence rate. So the convergence rate dropped below 2, so he stopped. And another thing to point out is that by default the plot is given around the von Mises stress, but this can be changed in this dialog as well, so you can set this to either a first principle stress, a third principle stress, or a displacement convergence. With all the knowledge acquired in the previous slides, let's come back to our weldment case and see how we can apply it in that case. So first of all, on the weld bead situation, when I apply H refinements and a stop criteria of 1% or 2%, I get a much more accurate result of the stresses. In this case, maximum stress is highlighted as being 73.9 ksi. If I compare this to the situation without the weld beads, I get a 76.4 ksi, so the value in this case is higher than the situation with the weld beads, and this is what we originally intuitively were expecting. So this is hopefully a good illustration of how you can correct an original wrong situation into more accurate results. Now that we have understood what convergence and P and H refinements is all about, let's put this in action on our weldment assembly. So I'm going here to the stress analysis environment, and let's first concentrate on the no weld situation. So when I created this particular analysis, I used the default solver settings, which means like no H refinements and a 10% stop criteria. If I would change values here, this would have absolutely no influence on the existing analysis. So we better change these settings in a different area of the product, and you can do so in the Convergence settings dialog. So this dialog has an immediate effect on your existing calculation. So let's say I'm asking for 3 age refinements and I ask for a 1% stop criteria. So this should make my calculation much more accurate than the default calculation. So let's kick it off and see what it brings to us. In case of the no weld situation, I now see that my maximum von Mises stress is 77 KSI. Remember this value because we need to compare. Before we move to the other analysis, I do want to show you the convergence plot. So in this case, we now have 3 extra steps over the P1 and P2 step, and you see that my convergence is far from ideal. I still have a 22% deviation between consecutive calculations. So with 77 KSI, let's go to the well beat situation. So I set the exact same settings here on the well beat situation, and we kick off this simulation as well. So we now expect to find a value which is at least smaller than 77 KSI because of the well beats. So we hope that the convergence will help us with this. We'll find out in a second. So we now have 73.77 KSI. If I look at the convergence plot, you see that first of all, my convergence rate is a little bit better than in the no well beat situation, and my KSI, my maximum von Mises stress, is below 77. So in principle, I should add extra steps in an attempt to get better results, but I think you get the picture how convergence and A refinements can give you more accurate results. As a summary, what are the important points that I would like you to take away from my presentation? Well, first of all, I wanted to be clear in your mind that you can do a lot of what-if iterations with this software during your design, and you could do this by using different materials, playing with the safety factor, and using the parametric table for optimization purposes. You could also obtain much more accurate results if you remember using the age refinement convergence technique. It doesn't come for free. You probably increase your calculation time and your mesh density, but the benefits are worth it. Thank you.